In this video, I would like to discuss Hooke's law and ideal springs. In the last example up here, we learned that the displacement of the bowstring was directly proportional to the force that was exerted by the archer. Well, Robert Hooke observed that, and for many objects, that the deformation or the change in the size or the shape of the object was directly proportional to the magnitude of the force that caused the deformation. So essentially, Hooke's law, which we now use, is an ideal law, by the way. It only really works under certain limits. States that the deformation, which is x, is directly proportional to the deforming force, which we usually write a little s there for spring force. Many of the springs that we deal with in class will obey Hooke's law, and we'll call them ideal springs. They'll obey Hooke's law as long as that spring is not stretched too far beyond its what we call the elastic limit. If it's stretched too far, then suddenly it will not return back to the original shape and no longer obey Hooke's law. So when a spring obeys Hooke's law and falls under this ideal condition, we call it an ideal spring. Each spring will have its own spring constant, which we use the notation of K, measured in newtons per meter, that depends on the stiffness of the spring. How hard you have to stretch or compress the spring. And in our formula, the X here represents the displacement of the spring from its equilibrium point. So when the spring is unstretched, we say that x equals 0 normally. So the force exerted by an ideal spring is given in this box right in here, which is on your AP formula sheet. Now you might be wondering, why is there a negative sign in front of the expression? Well, the negative sign indicates the direction of the force. So this minus sign right in here is a negative because it's a restoring force. It's always trying to pull in the opposite direction. So if you pull on the spring downwards, then if you have a block here attached here of mass m, then the spring force will be pulling upwards. Let's say you took the spring here and pulled it horizontally. It still maintains the same spring constant, but your hand is maybe pulling over here. This is your hand. And so you're applying an external force to the right. Well, the spring would then apply an equal and opposite force going in the other direction, F sub s. Because the spring force is to the left, and the displacement is, say, to the right, which we'll assume is positive, then we need to put a negative in front of our expression because it always is trying to restore this object and pull it back to where it was at equilibrium. Now, if we were to determine the work done for an ideal spring, we would first plot a force versus displacement graph. You would get this nice linear relationship between the force and the displacement. And then what we would do is calculate the area under the curve. So the work done from moving the spring from the initial position here of 0 to a final position x would be basically the area under the graph, which is the area of this triangle. So the base would be a distance of x, and the height would be this length here, which is equal to kx, as given by the equation f equals kx. And so this would give you 1/2 kx squared. And this would represent the amount of stored energy in the spring, which is called spring potential energy. More generally, if we start at an already pre-stretched position of, say, x initial and then end to a final position x final, then the work is defined as this, which is really 1/2 kx final squared minus 1/2 kx initial squared. 1/2 kx final squared would be the total area of this whole triangle here, whereas 1 half kx initial squared would be this area of this little white triangle in here. And if you were to subtract those two areas, you would end up with this area of this trapezoid. And this is what the work done would be equal to. And really what you're doing is you're finding the final spring potential energy minus the initial spring potential energy, which is equal to the work done. So now you know that the energy, which is made up of kinetic energy and potential energy, and kinetic energy is 1 half mv squared, but the potential energy could come in two different forms. We have the gravitational potential energy mgh, and now we have a spring potential energy 1 half kx squared if the problem involves ideal springs.